You followed the sky long enough to know that NASA doesn't stay silent without a reason. Not when something brightens 400 times in just 4 days. Not when an interstellar object shifts color 3 different times, as if its chemistry is waking up in stages. And not when jets begin erupting from its surface, holding steady even though the object is tumbling every 16 hours. Silence during anomalies like that is never accidental. That's why, the moment you saw the title tonight, something inside you stirred. NASA breaking their silence. At the same time, a new coronal mass ejection, one of the most energetic of this solar cycle, is moving directly toward 3I Atlas, not toward Earth, not toward any spacecraft, but toward a traveler from another star. And NASA has chosen this moment, of all possible moments, to finally speak. You're here because you sensed there was more beneath that timing. You're here because after a long day, after all the noise and obligations, there's a certain comfort in watching the universe play out a story too large for everyday worries. This is where your mind settles. This is where questions feel lighter and wonder feels steady enough to hold. You're not looking for drama. You're looking for something real, something grounded, thoughtful, and quietly extraordinary. So let's start with the fact that should have made headlines immediately. 3. Atlas didn't behave the way an interstellar comet should. Instead of fading as it approached the sun, it brightened violently. Instead of holding one stable color, it cycled through a spectrum that suggested shifting ices and unusual volatiles. Instead of forming a tail early, it held back until after perihelion, almost as if the sun's heat had to reach deep into its core to awaken it. And through all of that, NASA watched, collected data, and said nothing. You might remember checking the official channels, waiting for a press release, scanning the observatory updates, wondering why every comment came from amateur astronomers and independent researchers, while the agency with the most instruments remained quiet. You might remember thinking, this is strange. Why say nothing about something so unusual? Now finally, NASA has spoken, and the timing isn't lost on you, because right now, a wave of charged particles is leaving the sun and moving across space in a slow, majestic arc. A coronal mass ejection is not a beam or a blast. It's a rolling tide of magnetized plasma, millions of miles wide, carrying the imprint of the star that created it. When it reaches 3I Atlas, the interaction won't be explosive. It will be revealing. CME impacts can reshape tails, expose hidden structures in the coma, and reveal details that sunlight alone can't show. And if you're listening tonight, it means you want to understand what NASA has seen, what they've been studying in silence, and why this moment matters enough for them to break that silence now. The truth is that 3I Atlas arrived in our solar system at a rare moment. Not during a quiet year, not during a low point in the sun's cycle, but during the peak of solar maximum, when eruptions are more powerful, more frequent, and more capable of interacting with anything that crosses their path. Most interstellar objects pass through quietly, unnoticed except by those who go looking. This one didn't get that luxury. And somewhere inside you, that sparks curiosity, the kind that feels good to lean into, the kind that reminds you of being younger, flipping through astronomy books, or watching documentaries late at night because the universe has always been the one subject that makes you feel both grounded and free. You're here for that feeling again. And you'll get it. Tonight, you'll move through each stage of this story. You'll see how scientists tracked the object long before the public heard its name. You'll understand what the color changes meant, why the jets were so unusual, and how the object managed to survive perihelion intact. You'll understand why NASA waited to speak, and what the new CME could reveal when it washes over the object in the days ahead. Not in a rushed way, not in a sensational way, but slowly, clearly, and with enough space for your mind to wander without drifting too far. Because if the universe teaches anything, it's patience. Out there, nothing moves quickly. Not comets, not stars, not waves of solar plasma drifting through the void. And tonight, you get to follow that same pace. A steady pace. A quiet pace. A pace that lets you understand something extraordinary without feeling overwhelmed by it. So settle in. Let the atmosphere of the moment rise gently around you. Feel the weight of NASA's silence and the weight of their timing. Feel the quiet magnitude of a star reaching toward a visitor from another system. And feel the pull of your own curiosity bringing you here, to this moment, to this story. By the time you reach the end, you'll understand why NASA waited. You'll understand why this CME matters. And you'll understand why an object from another star, drifting silently across our sky, can still feel close enough to touch. You didn't need anyone to tell you that something unusual was happening. As September unfolded, you could see the changes with your own eyes in every new amateur image posted online. At first, 3i Atlas appeared as a faint red ember against the dark, a quiet, almost unremarkable visitor drifting into the outskirts of our solar system. But then, almost overnight, that ember transformed. The red hue softened, giving way to a pale green glow that wrapped around the nucleus like a thin, waking breath. And before anyone could adjust their expectations, the green shifted again, deepening into a cool, almost electric blue. By the time October began, the color transitions had become the first major point of debate. Interstellar comets weren't supposed to behave this way. They didn't normally display such rapid shifts in visible wavelengths, not without chemical triggers or structural changes. Yet here was 3i Atlas, rewriting its own appearance every time astronomers thought they understood it. Across forums, live stream chats, and astronomy circles, the same question repeated itself. What caused that color shift? You watched the discussions grow louder, but beneath the excitement was confusion. Respectful, curious, but undeniably real. Professional astronomers spoke cautiously, noting that different ices can sublimate at different distances from the sun. Amateurs offered side-by-side comparisons of nightly exposures, highlighting how quickly the hues evolved. And through all of this, something else emerged. The object wasn't just changing color, it was becoming brighter. Much brighter. Within a span of just 4 days, its brightness surged by a factor of 400. For most comets, such a jump would signal fragmentation, outbursts, or sudden breaks in the nucleus. But there was no visible debris, no signs of the object tearing itself apart, no dust storms large enough to account for the extreme brightening. What you saw instead was a quiet, almost graceful escalation, as though the object was simply stepping into the light a little more each day. And yet, Through the entire stretch of September and October, NASA said nothing. Other agencies released scattered notes, brief mentions, tiny updates buried in observation logs. But from NASA, the silence was absolute. Not a statement, not a press note, not even a casual acknowledgement. For many people, that silence became the loudest part of the story. In the online communities you follow, 3 questions kept rising to the top. Why the 400x brightening? Where is NASA in all this? Why haven't they said anything at all? Even the tone of the discussions reflected the curiosity of the moment. Some suggested that the extreme brightening meant the surface ices were more reactive than anything seen on typical solar system comets. Others speculated that maybe the object carried a mixture of volatiles unfamiliar to our environment, material formed around another star, under conditions we've never studied firsthand. A few proposed more exotic explanations: interstellar nitrogen ices, fragments from disrupted exoplanets, or objects formed in binary star systems where the chemistry is entirely different. Still, none of these theories fully explained what came next. Late October approached, and with it, perihelion, the tight swing around the sun that often becomes a stress test for any icy object. Temperatures soar. Radiation intensifies. Solar wind becomes a steady, unrelenting pressure. Many comets fracture during this passage. Some disintegrate entirely. But when 3I Atlas rounded the sun, it didn't break. It didn't dim. It didn't scatter dust into a debris trail. If anything, it looked calmer, clearer, more structurally intact than before. That moment sent the astronomy world into a quiet astonishment. A natural object from another star system had just endured one of the most punishing environments in our solar neighborhood, and emerged not weaker, but stronger. Even those who tried to remain cautious couldn't help but acknowledge that this was uncommon, very uncommon. And yet, NASA still said nothing. You could feel the tension each day as more amateur astronomers uploaded their images. Jets began forming, faint at first, then brighter and more defined. The coma expanded, taking on the shape of something alive with internal energy. Meanwhile, more telescopes around the world locked onto it. Backyard setups, university observatories, remote desert arrays. Everyone was looking. Everyone was talking. Everyone was waiting. But NASA kept its distance. And at that moment, the silence took on a different meaning. It didn't feel dismissive. It felt deliberate, strategic, as if NASA wasn't ignoring the object. They were watching it with the kind of caution you reserve for a phenomenon still writing the first chapter of its own story. You could sense it in the tone of the community posts, too. The longer NASA stayed quiet, the more it pushed people to ask deeper questions, not shallow ones. It encouraged analysis rather than frenzy, patience rather than panic. For you, the waiting became its own kind of ritual. At the end of each day, you checked new exposures, new data points, new time lapses of the coma expanding against the stars. You saw experienced observers dissect the early jets, trying to measure their angle and composition. You read explanations about exotic interstellar ices, crystalline structures, nitrogen plumes, fragmented volatiles, all layered theories attempting to catch up to an object that refused to behave predictably. And as those discussions grew, so did the anticipation. people began to say it openly. Everything changes on November 19th, the livestream date, the day NASA would finally speak. But before that day could arrive, something else happened. Something that shifted the tone of the entire conversation. A force older and more powerful than anything humans could orchestrate. A reminder that the sun is not just a light in our sky, but a restless star capable of shaping entire worlds with a single breath. A coronal mass ejection erupted from its surface, strong, fast, moving on a trajectory that would carry it directly toward 3I Atlas. And just like that, the month of silence gained new meaning. The questions grew sharper, the curiosity deeper, and the story you were following so closely took on a new energy, as if the universe itself had turned the page. And then, the sun intervened. When you think about the space around the sun, you usually imagine brightness, overwhelming, unforgiving brightness. But the reality is even more intense. Up close, the sun is not just light. It is heat, radiation, and a river of charged particles streaming outward in all directions. The solar wind thickens there, folding into turbulent layers of plasma that drift and collide like invisible tides. Temperatures soar high enough to strip atoms bare. Magnetic fields twist and snap. It's a place where only the most resilient objects can pass through intact. And on October 29th, that is exactly where 3I Atlas went. It approached perihelion quietly, without drama, without the spectacular flare-ups you might expect from a comet entering the sun's immediate reach. Observers around the world waited for signs of stress, fragmentation, cracks, sudden outbursts of dust. For familiar comets, this is the turning point where the nucleus begins to reveal its weaknesses. But 3I Atlas didn't behave like a familiar comet. It didn't waver or flicker or break apart. Instead, it slipped into the sun's radiance as if entering a bright, silent corridor. The closer it drifted, the harder it became to see. Solar glare washed over the cameras, drowning the faint streak of the object in a flood of white. Even spacecraft instruments struggled to catch a clean glimpse. The sun's presence dominated every pixel. And without the ability to observe its tail directly, people began to wonder whether the object had lost it, burned it away, or simply never had one to begin with. In reality, the tail was there. It was just hidden by angle, light, and distance. You picture it now. An interstellar traveler passing just close enough to feel the sun's breath on its surface. Ices sublimating, gases releasing, but doing so within the intense glow, where even the tiniest detail becomes invisible to us from a distance. There's something calming in imagining that moment, not as a violent interaction, but as a quiet immersion into the heart of the solar system. And then, something remarkable happened. Nothing. There was no collapse, no disintegration, no sudden fade. Against all odds, 3I Atlas survived perihelion. For objects formed in another star system, objects that have spent millions, perhaps billions of years drifting through cold interstellar space, perihelion encounters are rare events. To pass this close to any star is unusual. To endure the encounter without shattering is even more unusual. Survival is the exception, not the rule. And that's what makes this moment so extraordinary. You can almost feel the shift in the global anticipation that followed. The moment the object re-emerged from the solar glare, the astronomy community leaned in. Images began to trickle in from observatories and spacecraft, each one clearer than the last. And in those first new frames, something was different. The object looked brighter, more defined, more active, as though something inside it had changed during its time near the sun. Many described it as an awakening. Before perihelion, the object appeared subdued, dim, quiet, a distant enigma. After perihelion, everything sharpened. Jets became visible, extending from the nucleus like delicate threads of gas. The coma expanded, glowing with a fresh layer of energized particles. Even its rotation seemed more apparent, creating subtle asymmetries that hinted at deeper structures beneath the surface. You find yourself imagining it in slow motion. 3 Atlas, entering the sun's inner domain as a silent ember, then drifting out again like a lantern that had just been lit. There's a sense of awe in picturing it, an object older than our planets, shaped by a star we've never seen, now carrying the sun's imprint as it journeys away. And yet, alongside that sense of awe, comes a more analytical curiosity. Why did it survive? What combination of structure, composition, and origin allowed an interstellar body to tolerate such extreme conditions without fracturing? Was the nucleus larger than we expected? Was its chemistry different, perhaps stronger or more cohesive than typical solar system comets? Or was it simply lucky, meeting just the right balance of heat and distance? These questions don't produce anxiety. Instead, they settle into your mind like gentle ripples. Quiet mysteries you want to follow as the story continues. And the more you consider them, the clearer it becomes that perihelion wasn't just a test of survival. It was a turning point, a change in the object's behavior, a moment where dormant materials deep inside finally met enough warmth to react. This is where the story deepens. Because perihelion didn't just spare 3I Atlas, it prepared it. The sun's heat may have softened the outer layers. It may have opened new fissures. It may have activated fresh channels for jets to form. And as those gases began to vent outward, even subtly, they created pathways that would later interact dramatically with the coronal mass ejection already moving in its direction. Perihelion didn't complete the story. It set the stage for what the CME will uncover. And when you look at it through that lens, the survival of 3I Atlas becomes something more than a lucky outcome. It becomes a necessary step, an essential moment that allows everything still to come to make sense. Because if the object had broken apart, if it had simply evaporated into dust, the CME would have had nothing to illuminate, nothing to reshape, nothing to reveal. Instead, it left perihelion intact, glowing, awakened. You're watching a traveler from another star that touched our sun and lived. And now that it has tasted the sun's warmth, it carries new features into the path of the oncoming solar wave, features that only a post-perihelion object can display, features that will tell us more about its structure, its origins, and the strange chemistry it holds. You can feel how this moment fits into the larger story. The object survived the fire, but survival was only the beginning. By the time 3I Atlas emerged from perihelion, something else had already started moving in its direction. Something vast, invisible to your eyes, but unmistakable in the data. It began on the surface of the sun, in a region you've heard about many times over the past year, one of the most active sunspot groups of this solar maximum, the same region that had already sent waves of charged particles toward Earth, lighting up polar skies with auroras brighter and more widespread than usual. On that particular day, the region flared again. Magnetic fields twisted until they snapped, releasing a burst of energy that rolled outward as a coronal mass ejection, a CME. Not the largest of this cycle, not the most dramatic in terms of speed, but powerful enough to carry an immense cloud of solar plasma away from the star and out into space. From above the plane of the solar system, models showed the wave expanding like a slow-motion ripple, spreading across a darkened pond. And right there, just off the edge of the ecliptic, sat the trajectory of 3I Atlas. You can imagine the view from that perspective. The sun at the center, still blazing, the orbits of Earth and Venus looping as pale rings around it. And slightly above that flat disk, the path of a single interstellar object crossing through, a thin, faint line against the model's grid. As the CME plume expands, that line and the wave begin to converge. What the model showed was simple and undeniable. The CME and 3I Atlas were headed for the same point in space. Predictions placed the interaction around November 22nd, near midday in universal time. Not a precise impact in the sense of a collision, but an overlapping of regions, a moment when the densest part of the CME would sweep across the area occupied by the object and its coma. And while many solar storms are modeled every year, it is rare that one lines up so clearly with an interstellar visitor. Rarer still, when that visitor has just survived perihelion and awakened into a more active, jet-filled state. To understand why this matters, it helps to think less in terms of explosions and more in terms of waves. A CME is not a bullet. It's more like a slow, swelling tide of plasma. Electrons, protons, and heavier ions all bundled together within twisted magnetic fields. As it moves outward from the sun, it doesn't travel as a solid front, but as a vast, expanding bubble with different densities and structures embedded inside. If you could sit in space and watch it go by, you wouldn't see a flash. You'd feel a gradual change in the environment around you, the magnetic field bending, the particle density rising, then falling again as the wave passes. Now place 3I Atlas inside that picture. Picture the object not as a solid rock alone, but as a tiny nucleus wrapped in a huge, delicate envelope of gas and dust, the coma, stretching hundreds of thousands of kilometers in every direction. Picture a faint tail extending away from the sun and a subtle, more complex pattern of jets and streams that do not always behave as normal comets do. Then imagine that entire structure being washed over by the moving plasma wave. This is where the physics becomes quietly beautiful. As the CME approaches, its magnetic field begins to interact with the plasma environment around the object. The coma is already full of ionized particles, atoms and molecules that have lost or gained electrons under the influence of sunlight and the solar wind. Those ions respond strongly to magnetic fields. When the CME arrives, it drags its own magnetic structure through that region, distorting the local field lines, compressing some areas, stretching others. In some cases, this can cause dramatic changes in the shape of a comet's tail, bending it, twisting it, or, in rare instances, disconnecting it entirely. A tail disconnection event is one of the more surreal phenomena in cometary science. From a distance, it looks as if the comet has suddenly dropped its tail, leaving a piece of itself hanging in space while a new tail slowly grows behind it. But what actually happened is that a change in the surrounding magnetic environment severed the plasma connection between the comet and its tail. Like cutting a rope in a strong wind, the tail doesn't vanish, it simply loses its anchor and drifts away, while fresh gas and dust begin forming a new one, aligned with the changed conditions. For 3I Atlas, the prospect of such an event is particularly intriguing. Its tail and jets are already behaving strangely. Some of its emissions point sunward, some remain narrow and sharp even as the object rotates. The coma itself is unusually large for an object of its apparent size. A CME sweeping through this environment is not just a disturbance, it's a probe in a sense, a natural experiment that may reveal hidden structures in the plasma surrounding the object. And that's where your curiosity settles. Not in fear, not in alarm, but in a calm, focused interest. What will this wave uncover? Will the tail bend, fragment, or remain stubbornly intact? Will the jets brighten or fade? Will the coma compress, showing new internal patterns? Or will it expand further as charged particles are swept up and redirected? There's another layer to this moment that you can't ignore. While many people spent their attention on storms headed toward Earth, this particular CME wasn't aimed at our planet at all. It sailed away from our line of sight, barely affecting us directly. For most of the world, it passed without notice. No big headlines, no widespread auroras. Yet out there, beyond our concern, it was headed almost straight for an interstellar object that has already defied expectations more than once. That combination, quiet on Earth, significant out there, is part of what makes this event so compelling. It feels like a private chapter in the story of 3I Atlas, one you get to follow closely, while the rest of the world carries on with everyday concerns. It's a reminder that the universe doesn't revolve around us, even when we're not looking. Stars flare, waves move, and visitors from other systems continue their journeys, whether or not anyone is watching. But NASA is watching. And that brings you back to the earlier question that has been echoing in your mind. Were they waiting for this? Were they gathering data, tracking the object through perihelion, watching its coma and jets evolve, and then marking their calendars, not just for the live stream on November 19th, but for the CME interaction on the 22nd as well? It's not that they engineered the timing. The sun chose that. But they could recognize what it meant. A CME interacting with an interstellar object offers a rare chance to study how material from another star system responds to one of the most dynamic forces in ours. It's a moment when theory and reality overlap, when models of plasma physics meet actual measurements taken from across millions of kilometers. You can think of the CME as an ocean wave and 3I Atlas as an iceberg drifting through that sea. The wave doesn't destroy the iceberg, but it does reveal its behavior, how it rocks, how it sheds pieces, how the water flows around and behind it. In the same way, the CME may reveal how firmly the jets are anchored, how dense the coma truly is, and how the object's own outgassing shapes the surrounding space. And as you picture that encounter in your mind, a slowly moving wall of plasma reaching the outskirts of the object's environment. You feel something like quiet anticipation. Not adrenaline, not fear, just a calm readiness to see what changes, if any, will appear in the images and measurements that follow. You know you won't get all the answers immediately. Data takes time to process. Models take time to refine. Interpretations take time to settle. But that's part of the appeal. This isn't a one-night spectacle. It's a slowly unfolding chapter in a much larger story, and you're listening to it in real time. Soon, you'll explore the aftermath. You'll look at how the tail and jets behaved. You'll hear what observers noticed in the nights after the predicted interaction. You'll see whether the object's unusual characteristics became clearer under the influence of the solar wave, or whether it simply absorbed the event and continued on, unchanged, deeper into the inner solar system. For now, it's enough to know that the wave is moving, the object is waiting, and the instruments are watching. But to see the impact clearly, we must watch what came after. You remember the anticipation leading up to November 19th? After weeks of watching the object change color, brighten sharply, survive perihelion, and drift toward the oncoming CME, there was finally a moment when the silence would break. Not through leaks or speculation, but through NASA itself stepping forward, speaking directly, and offering something solid to hold on to. And as the live stream began, you could almost feel the collective exhale from everyone who had been following the story closely. From the very start, one detail stood out. NASA didn't call 3I Atlas a possible interstellar object. They didn't hedge or offer alternative classifications. They used a phrase that carried weight and certainty: interstellar comet. Those two words settled something fundamental. They placed the object firmly in the lineage of the rare visitors that had passed through our solar system before. Oumuamua in 2017, Borisov in 2019. But with its own behavior and identity. Hearing NASA use that term was a moment of quiet validation, a recognition that the mystery unfolding in front of you was not imagined or exaggerated. It was real. The tone of the live stream wasn't dramatic. It wasn't meant to shock or excite. It was steady, measured, almost comforting. NASA walked through their observations with the calm assurance of people who understand the scale of what they're discussing. They spoke about the trajectory, the coma expansion, the unexpected brightness, and the complex behavior of the jets. Yet they did so in a way that kept the moment grounded, scientific, and accessible. Instead of offering a rapid-fire list of anomalies, they offered clarity. And then came the images. They showed data sets from different missions, wide field frames from Hubble, coronagraph silhouettes from SOHO, and the long-anticipated high-resolution captures from the Mars Reconnaissance Orbiter. Seeing the object from multiple angles, across multiple instruments, gave it a dimensionality it hadn't had before. Its environment began to make more sense. The layers of dust and gas became clearer. The shape of the coma, the subtle asymmetries, the sunward streams. Everything came into focus in a way that felt almost intimate. But it was the high-rise images that held your attention most. They didn't show a clear nucleus. There was no crisp outline, no sharp-edged core you could point to and say, "There it is." Instead, there was a concentrated point of brightness, surrounded by a gradient of diffuse light. It was a small thing, a speck really, but it carried the weight of an entire object wrapped in its own glow. Under the right filters, you could see faint jets emerging from that central region. You could see how the coma thickened on one side and tapered on the other. You could sense shape without truly seeing it. And that was precisely what fascinated you. Why was NASA showing images where the nucleus looked so unresolved? Why hadn't they used sharper enhancements or more aggressive filtering? Why did the brightest point remain so indistinct? The live stream didn't say the words directly, but the implication was clear enough. The nucleus might be extremely small, or extremely well hidden, or simply more difficult to isolate because of the object's brightness and the sheer size of the surrounding coma. NASA didn't speculate. They didn't jump ahead. They simply showed the images and let them speak for themselves. You felt both relief and curiosity in that moment. Relief because nothing in the presentation leaned towards sensational explanations. Curiosity because the gaps in the data hinted at deeper layers still to be revealed. The presenters discussed the unusual behavior without leaning into the fantastical. They addressed the brightening, the jets, the color shifts, and the survival through perihelion. They connected these behaviors to known cometary physics, acknowledging that 3-eye atlas fits within a natural framework, even if the details stretch the edges of what we typically see. There was no talk of impossible maneuvers, no references to artificial structures, no suggestions of unknown technologies. If anything, they bent over backward to keep the explanation grounded. That steadiness felt reassuring, especially if you've spent years watching how easily cosmic stories can drift into exaggeration. And yet, under that calm tone, the data still carried mystery. The way the jets held steady despite the rotation, the way the coma thickened after perihelion, the way the brightening spiked then stabilized, the way the object carried no visible fragments, no debris fields, no obvious signs of stress. These weren't things NASA dismissed. They simply didn't rush to conclusions. They let the evidence breathe. One question lingered in your mind as you listened. Why didn't they address the nucleus size more directly? And why skip the conversation about non-gravitational accelerations? The subtle pushes and pulls that sometimes hint at unusual outgassing patterns. You notice their avoidance, and it made the live stream feel less like a closing statement and more like the opening chapter of something they plan to revisit once the data from the upcoming CME interaction became clearer. Perhaps they didn't want to draw premature conclusions. Perhaps the images weren't sufficient to make strong claims. Or perhaps, in a moment where the world was watching, they chose to stay with the facts they could fully support. Whatever the reason, their approach made you lean in a little more. Sometimes, what isn't said can deepen your interest just as much as what is. By the end of the live stream, you felt steadier. The haze of rumors had lifted. In its place was something more grounded, more scientific, more open-ended. NASA had confirmed the object's identity. They had shown the data. They had acknowledged the anomalies without overstating them. And they had positioned themselves, quietly and carefully, to share more once the next chapter unfolded. But images alone don't tell the full story. And as you sit with that thought, you realize that the questions you still hold, about the nucleus, about the jets, about the strange behavior, will lead you naturally into the deeper mysteries still waiting to unfold. One of the first things you notice when watching 3I Atlas evolve after perihelion is that its behavior doesn't fit neatly inside the patterns you're familiar with. You understand how comets work. You've seen enough over the years to know what should happen when a tumbling nucleus vents gas into space. The jets should blur. They should fan outward. They should smear into soft, uneven arcs as the nucleus rotates. That's the standard picture. Predictable, logical, and supported by decades of observation. But 3I Atlas refuses to follow that script. The rotation period alone should create chaos. Estimates place the spin at roughly 16 hours, and the object appears to be tumbling rather than spinning cleanly around a single axis. In a situation like that, outgassing should become irregular. Jets should flicker in and out of visibility as the vents rotate into shadow. The coma should thicken unevenly on one side and scatter on the other. Instead, what you see is something almost counterintuitive. Narrow, persistent jets that remain defined far longer than expected. They don't blur with rotation. They don't collapse into soft plumes. They hold their shape. It's as if the jets belong not just to the object, but to the space around it. And then there's the anti-tail. If you've followed comets long enough, you know how rare that phenomenon is. A tail pointing toward the sun should feel backward at first glance, as if the comet were somehow defying radiation pressure. But anti-tails are not impossible. They happen under precise geometric conditions when dust spreads along the orbit in a thin sheet, and from Earth's angle appears to point sunward. The conditions need to be just right. The timing matters. And even then, it's something you see only in a handful of comets, often for a brief window of days. For 3I Atlas, the anti-tail appears sharper and more stable than expected. It doesn't sweep unevenly or fade quickly as the object rotates. Instead, it creates a narrow, elongated structure that seems to anchor itself in the surrounding plasma. That stability raises questions, ones that push you deeper into the physics of ionized environments. Because while the nucleus of 3I Atlas is only a few kilometers across, the plasma envelope around it could stretch hundreds of thousands of kilometers. And inside that massive region, magnetic gradients and charged dust begin to shape the behavior of gas in ways that aren't always intuitive. To understand why the jets maintain their form, imagine the ionopause, the invisible boundary where the solar wind meets the outflow of ions from the object. For most comets, this boundary shifts and fluctuates as the solar wind changes. For 3I Atlas, the ionopause appears unusually large and stable, possibly due to the object's recent perihelion passage. When the sun heats dormant ices deep beneath the surface, the resulting gas release can be strong enough to create a thick, extended region of ionized particles. Those particles form channels, and channels can guide jets the way grooves guide water. Magnetic gradients play a role too. The solar wind carries embedded magnetic fields, twisting and shifting as they travel. When those magnetic structures meet an ion-rich environment like the one around 3I Atlas, they can create long-lived paths, lanes where charged particles are funneled, and where outgassing from the nucleus is naturally directed. Even if the nucleus rotates, The surrounding environment can hold the jets in shape, smoothing out the inconsistencies that would normally appear. Then there's the matter of dust charges. Tiny particles expelled from the nucleus become electrically charged under ultraviolet radiation. Those charges influence how dust aligns within the surrounding magnetic field. Under the right conditions, dust can form rigid-looking structures that seem anchored in place rather than smeared by rotation. What you observe as a stable jet may be the visible surface of a dust stream, shaped and held in alignment by the deeper plasma structures around it. You've seen something like this before. If you watch the Rosetta mission's footage of Comet 67P, you might remember how jets could appear surprisingly narrow, almost laser-like, even though the nucleus rotated. Scientists later found that some of these jets were the result of stable plasma channels surrounding the comet. Channels that seemed impossibly organized given the chaotic nature of the gas emissions. In that sense, 3I Atlas isn't breaking the rules. It's demonstrating those same rules under more extreme interstellar conditions. But here's where the curiosity grows. The plasma envelope surrounding 3I Atlas appears to be far larger relative to its nucleus than what you see in most comets. In some frames, the effective region influenced by the object spans hundreds of thousands of kilometers, large enough that the nucleus becomes more like a source feeding an environment instead of controlling it directly. And when the environment becomes that large, stability no longer depends solely on the rotation of the solid core. It depends on the structure of space itself, the ion flows, the magnetic pathways, the balance between solar wind pressure, and the outgassing of the object. This is where the mystery deepens. The space around the object might be shaping the jets more than the nucleus itself. It's an idea that feels strange at first, but the more you let it settle, the more it begins to make sense. You're no longer looking at a comet behaving on its own terms. You're looking at a system, a moving interaction zone between material from another star and the dynamic forces of the sun. And once you see it that way, the behavior becomes less impossible and more mesmerizing. The jets remain narrow because the plasma envelope remains narrow. The anti-tail appears stable because charged dust finds stable paths to follow. The rotation doesn't smear the jets because the environment compensates, holding them in alignment the way the magnetic field of a river guides its own currents. Still, questions linger. Why is the environment so large? Why are the plasma structures so well organized? And why does the anti-tail remain visible longer than expected? You feel the curiosity sharpening, but not in a way that disrupts the calm of the moment. It's a quiet pull, a desire to understand something rare and beautiful without rushing the explanation. Because you know there's more coming. You know that the strangeness of the jets is only one piece of the larger puzzle. And you can sense, even now, that the story will circle back to these features when the origins of the object are explored. To understand its behavior, we must understand the space around it. If there's one question that has quietly guided every discussion about 3I Atlas, it's the size of its nucleus, not its color, not its jets, not the shape of its coma. Those things matter, of course, but they all come second to a single measurement: how large the solid core actually is. That number shapes everything else. It determines the object's mass, its ability to withstand heating, the rate at which it loses material, and how long it can survive as it travels from one star system to another. And yet, for all the images, all the data, and all the careful modeling, the true size of the nucleus remains strangely elusive. NASA's livestream didn't answer the question directly, and that alone deepened your curiosity. You remember the first early estimation from Hubble, a nucleus around 2.8 kilometers across. That would place 3I Atlas firmly in the category of small to medium comets, large enough to sustain outgassing for months, small enough to be vulnerable to significant mass loss as it nears the Sun. A nucleus of that size could explain some of the brightening, especially if fresh ices were exposed. It would also be consistent with the faintness of the earliest images and the way the object appeared before perihelion. But then came the models suggesting something very different. Some place the upper estimate not at 3 kilometers, but at 10, or even 50. A 50-kilometer nucleus would be extraordinary, larger than Hale-Bopp, larger than most long-period comets ever documented. If the nucleus were truly that massive, the physics would change completely. It would spin more slowly. It would resist fragmentation more easily. It would carry enough thermal inertia to survive perihelion with surprising stability. It would also suggest an origin in a region of its home system where large icy bodies form, perhaps in the outer reaches of a young protoplanetary disk. But that leads to the obvious question. If 3I Atlas truly had a massive 50-kilometer core, how could it have wandered the galaxy for billions of years without breaking apart? Objects that large face collisions, gravitational disruptions, and internal stresses as they age. For something that big to travel interstellar distances intact, it would need a combination of strength, composition, and quiet luck that feels almost improbable. On the other hand, if the nucleus is closer to 3 kilometers, another problem emerges. How has it not shed more mass? The brightness jumped 400 times before perihelion. Jets formed after perihelion. The coma expanded dramatically. A small nucleus releasing that much material should show signs of erosion, fragmentation, shedding, uneven outgassing. But no such obvious damage has appeared. The object looks whole, structured, consistent. If it's small, it's extraordinarily durable. If it's large, it's extraordinarily well preserved. Either answer creates fascination. This is where the high-rise images matter. Even though they didn't show a crisp nucleus, they offered the clearest constraints we've had so far. The small, bright core at the center of the coma was unmistakable, visible even through the haze of reflected light from the surrounding dust. But the brightness itself made measurement difficult. If the surface is covered in fresh ices, the reflectivity can mislead the models. If jets are directed toward the camera's line of sight, they can contribute to the central glow as well. And then there's the main complication. The coma is enormous, nearly 700,000 kilometers across at its widest estimates. When an object is enveloped in a structure that large, the nucleus becomes a hidden point inside a glowing cloud. Measuring it isn't like measuring a rock. It's more like estimating the size of a grain of salt inside a snowstorm. By looking at the shape of the storm itself, the coma dominates the image. The nucleus becomes a guess within a guess. This difficulty explains why the estimates span such a wide range. Small nucleus, possible. Large nucleus, also possible. The data points, brightness, coma size, jet strength, and rotation, can support either scenario depending on the assumptions you plug into the models. Some researchers argue that only a larger nucleus could explain the stability of the jets. Others suggest that a small nucleus with highly volatile ices could produce the same appearance. The absence of strong non-gravitational accelerations, often used to estimate mass loss, complicates things further. Without clear deviations in motion, it's harder to know how much material is actually leaving the surface. As you listen to the details and weigh the possibilities, you feel a quiet kind of fascination, not the frantic curiosity that keeps you awake, but the deeper, steadier wonder that lets your mind settle while it explores a question without urgency. You don't need the answer immediately. The fact that the range remains uncertain is part of what makes the object compelling. It leaves space to imagine both extremes, the tiny survivor and the massive wanderer. You picture each possibility. If the nucleus is small, then it is a miracle of endurance, a compact, tightly bound fragment that has somehow resisted erosion across unimaginable distances. If the nucleus is large, then it is a relic from a robust planetary nursery, ejected during the formation of another solar system and preserved almost perfectly as it drifted through the cold, interstellar dark. Either way, that single measurement, its size, carries implications that ripple through every other aspect of the story. It influences how the jets behave, how the coma forms, how the object interacts with the solar wind, and how it will respond to the CME sweeping toward it. It shapes the physics, the chemistry, the thermal balance, and even the long-term trajectory of the object. And although NASA didn't give a definitive answer in the live stream, they gave something else: the data needed to narrow the possibilities. The high-rise images didn't reveal the nucleus directly, but they did place boundaries on the coma's brightness distribution. They offered a starting point. The next steps, analyzing the post-CME environment, tracking the jets over time, measuring the coma's density, will bring the estimate closer to the truth. For now, all you can do is sit with the possibilities. And somehow, the uncertainty feels soothing. The universe doesn't rush its answers, and neither do you. There's a calmness in imagining that even the most advanced instruments we have still struggle to capture something so small within something so vast. And that single number could redefine everything we know about it. When you follow an object like 3-Eye Atlas across the sky, it's easy to think only about what it's doing now, how it brightens, how it behaves near the sun, how its coma grows and its jets form. But the deeper fascination, the part that settles into your mind long after you've stepped away from the telescope, is the question of where it came from. Not its path into our solar system, but its true origin, its birthplace, the environment that shaped it, the star it once orbited. That question is larger than any one observation. It stretches across billions of years and unimaginable distances. And even though we may never know the full answer, the science offers several possibilities worth exploring slowly, carefully and with a sense of calm wonder. The first possibility is also the most straightforward. 3I Atlas may be a traditional interstellar comet ejected from the cold outer disk of another planetary system. Picture the distant reaches beyond a star, regions analogous to our Oort cloud, filled with icy fragments left over from the formation of planets. These regions contain materials untouched by heat, frozen since the earliest days of their system's creation. Sometimes, gravitational nudges from passing stars or nearby planets eject one of these fragments. They drift into interstellar space like seeds carried on a cosmic wind. If 3I Atlas originated here, it would be made of familiar materials: water ice, carbon dioxide ice, methane, ammonia, but its exact proportions might differ, shaped by the chemistry of its parent star. That difference alone could account for some of its unusual behavior, its shifting colors, its late-blooming coma, its turbulent jets. This hypothesis fits comfortably within what we know. It doesn't require rare events or exotic processes. It simply relies on time, gravity, and distance. The second possibility is more dramatic. Some scientists have suggested that 3I Atlas could be a fragment of a super-Earth, an icy mantle or crust torn from a much larger world. In some planetary systems, collisions between young planets or gravitational disruptions from massive neighbors can hurl pieces of rocky or icy layers into space. Over time, those fragments cool, darken, and drift outward until they are no longer bound by their star. If 3I Atlas is such a fragment, its composition would be unlike any typical comet. It might contain high-pressure ices, exotic carbon structures, or crystalline materials formed deep beneath a planetary surface. This could explain why it seems to survive heating so well, why its jets behave strangely, or why its coma structure feels different from the ones we usually see. But this hypothesis raises its own questions. Fragments like this are rare. They require violent events in early planetary systems, and they often don't remain intact for billions of years unless they are unusually strong. Still, the idea carries a quiet intrigue. The possibility that the object drifting through our solar system is the remnant of a world that no longer exists. A third possibility reaches into the peculiar dynamics of binary star systems. Around many pairs of stars, the gravitational forces weave complicated, overlapping paths. These systems generate planetesimals, small building blocks of planets that can be ejected far more easily than in single-star systems. One stray nudge at the wrong moment, and a young worldlet is thrown out completely, set adrift between the stars before it even has a chance to grow. If 3I Atlas is such a planetesimal, its materials may reflect the chemistry of a dual-star environment. Densities shaped by fluctuating temperature cycles, ices formed under alternating light sources, dust grains crystallized by two different stellar spectra. Such an object could behave strangely under sunlight, not because it is exotic, but because its baseline conditions formed under a different set of rules. If this is the case, the object you're watching might be something like an unfinished planet, a celestial building block that never found a home. And then there is the fourth possibility, the one that feels both mysterious and oddly grounded. 3I Atlas could be a dark comet carrying exotic volatiles not commonly found in our region of space. Dark doesn't mean artificial or unusual in a sensational way. It refers to comets with high concentrations of complex carbon compounds, metals, or nitrogen-rich ices that absorb sunlight instead of reflecting it. Some interstellar ices form in cold molecular clouds where temperatures drop so low that rare compounds become stable. When objects like this enter a warm stellar system, they behave differently. Their surfaces crack in unexpected patterns. Their color changes reveal transitions between exotic ices. Their outgassing phases start later or occur unevenly. This hypothesis explains several features of 3I Atlas without stretching the science too far. It accounts for the brightness surge, the delayed coma formation, and the odd stability of the jets. It also fits with the idea that its plasma environment behaves differently, because different materials ionize differently when exposed to sunlight. But here's where the puzzle deepens. None of these hypotheses fully explains everything. Each one fits some details, but not all. The interstellar comet hypothesis accounts for the general behavior, but not the sharp jets. The super-Earth fragment idea explains strength and stability, but struggles to match the smooth brightness curve. The planetesimal origin fits the structure, but not the thermal resilience. And the dark comet model accounts for the shifts in color, but not the unusually large coma size. Instead of narrowing down, the possibilities fan outward, each offering part of the picture, but leaving enough unaccounted for to keep the mystery alive. And this is where comparison becomes helpful. Oumuamua, in 2017, had no visible coma and accelerated slightly without releasing detectable gas. Borisov, in 2019, behaved more like a typical comet, but fragmented rapidly. 3I Atlas sits somewhere between them, more comet-like than Oumuamua, more stable than Borisov, but carrying its own bizarre signatures. The color shifts, the late blooming, the organized plasma environment, the massive coma, the jets that seem to lock into magnetic channels rather than the rotation of the nucleus. It's this interplay between the familiar and the unfamiliar that creates the quiet fascination you feel now. The plasma environment alone hints at unusual chemistry. Different materials ionize in different ways. Different volatiles respond differently to ultraviolet light. If 3I Atlas carries ices that formed under conditions we rarely encounter, then its behavior under sunlight, solar wind, and the recent CME will deviate accordingly. Not because it is unnatural, but because it comes from a place where the rules of temperature, radiation, and chemistry were written differently. That's the beauty of following an object like this. You don't need it to be extraordinary in a sensational way. You don't need it to defy physics or rewrite cosmology. It is already remarkable simply by existing, by leaving one system and entering another, carrying the fingerprints of its origin across distances larger than language can describe. Every observation you collect from it is a small message from another corner of the galaxy, carried not in words, but in chemistry, structure, and motion. You breathe a little deeper as the possibilities settle. They don't crowd your mind. They expand it, gently. You don't need a final answer tonight. This is a mystery built on patience. Evidence will accumulate. Models will improve. Data from the CME interaction will reveal more. And though its past remains hidden behind uncountable years of drifting through darkness, its behavior now, under our sun, inside our instruments, within our understanding, offers clues that will get us closer. Its past is unknown, but its future is visible tonight. When the CME finally swept past the region of space occupied by 3I Atlas, there was no dramatic flash, no sudden transformation, no moment when the universe announced what had happened. Instead, the changes, if any, unfolded quietly, the way most things do in the vast calm of the solar system. And in the nights that followed November 22nd, you found yourself watching closely, not for spectacle, but for subtle shifts, small clues, gentle signatures of interaction. The first thing observers noticed was the shape of the tail, or rather, the way it seemed to reorganize itself. Before the CME arrived, the tail of 3I Atlas had already shown complex structure, narrow sections, faint layers, and the unusual anti-tail pointing sunward. After the CME, some amateur images hinted at a kind of renewed sharpness, not necessarily brighter, but clearer in form, as if the wave of plasma had brushed away the looser dust and left behind a more defined spine. This happens with comets from time to time. When a CME compresses the ion environment, it can strip older structures and allow new ones to form more clearly. And when your viewing angle aligns just right, those refreshed structures can appear more vivid than they were before. Some observers reported faint signs of a bend in the primary tail, a subtle curvature that wasn't obvious earlier in November. It didn't look like a dramatic disconnection event, the type where a comet seems to leave its tail behind. Instead, it looked more like the tail had absorbed a temporary push from the disturbed magnetic field and then settled into a slightly different orientation. Whether this was the direct influence of the CME or simply the combined effect of solar wind variability is something researchers will sort out over the coming weeks. But even the possibility of a structural shift adds a soft layer of intrigue to the story. Then came the jets. Observers comparing images from mid-November with those captured after the CME noticed that the jets seemed a bit stronger in some frames, or at least more pronounced against the thinning coma. It's possible that the plasma compression made the inner region more transparent, revealing jets that were already there. It's also possible that the CME briefly increased ionization, making some features stand out more clearly. When charged particles sweep through a comet's environment, they can enhance contrast, sharpening the edges of active regions. The jets of 3I Atlas have always been unusually stable, guided by the surrounding plasma. After the CME, that stability seemed to persist, but with subtle shifts in angle or brightness that hint at a renewed flow of ionized material. What stands out most, though, isn't the professional data. It's the amateur observations. There's something quietly beautiful about that. Space agencies provide the high-precision measurements, but the day-to-day visuals, the incremental changes, the small surprises, they often come from people standing under night skies with telescopes in their backyards. After November 22nd, dozens of amateur astronomers uploaded new images of 3I Atlas. Some captured slightly sharper tails. Some caught faint hints of jets. Some simply recorded the object as it continued its path, unchanged in its broader appearance, but subtly different in texture. These amateur images matter because they catch the object when professional instruments are not pointed at it. They capture variation over hours instead of days. And in a moment when the object has just been brushed by a solar wave, that kind of continuous coverage becomes priceless. The CME may have passed, but its influence could linger briefly in the density and structure of the surrounding plasma. Amateurs become the eyes that fill in the gaps between the major data sets. One of the more interesting notes from early post-CME images is that the tail appears more visible in certain wavelengths and angles, especially when observers position themselves so that sunlight scatters off the fresh dust grains. That scattering effect can mimic brightness increases, even if the comet hasn't released a significant amount of new material. What looks like a brightening may actually be geometry. The sun, the dust, and the observer aligning in a way that highlights structures that were invisible the week before. And while these effects may seem small, they form the quiet heart of cometary science. A tail that bends slightly, jets that sharpen, a coma that smooths at its edges, a plasma environment that shifts density for a short time after a solar wave passes. Each change is subtle, but each one tells a story about how material from another star responds to the forces of ours. This is where the calm fascination settles in. You're not watching a dramatic transformation. You're watching the universe adjust itself after a brief disturbance. A dust cloud reshaped, a jet rechanneled, a tail realigned. It's gentle, almost meditative. And yet, within those soft shifts lies something valuable. The CME, for all its calm passage from Earth's perspective, may have acted like a probe, momentarily lighting up structures that were previously hidden. It may have drawn out features that were there all along, shaping them just enough to reveal their form. Because even though the CME interaction has already come and gone, and even though the object continues on its path without fanfare, you can't escape the sense that something about its environment is a little clearer now. The shock didn't break it. The wave didn't distort it beyond recognition. Instead, the interaction added definition, like gently brushing dust from the surface of a sculpture. But the story doesn't end with impact. When you pause to consider 3I Atlas not just as an isolated phenomenon, but as part of a growing lineage, something in the story widens. It stretches beyond this year, beyond this solar cycle, beyond the brightening and the jets and the CME. It connects to a deeper arc, one that began only recently in human history, yet reaches backward and forward across cosmic time. Before 2017, no one had ever seen an interstellar object pass through our solar system. The idea existed in theory, in simulations, in the quiet corners of astrophysical models, but never in observation. And then the universe opened that door. The first visitor was Oumuamua in 2017. It swept in silently from above the ecliptic, small, faint, and fast. So fast that by the time we realized what it was already leaving. Oumuamua puzzled scientists with its lack of a visible coma and its gentle acceleration away from the sun, as if sunlight alone were nudging it along. It was quiet, enigmatic, and fleeting, an object that left more questions than answers. But it marked a beginning. It proved that the galaxy sends travelers our way, even if we spot them only at the last moment. 2 years later came 2I Borisov. Unlike Oumuamua, it behaved more like a typical comet, bright, volatile, active. It carried a clear coma, a shining tail, and the unmistakable signatures of sublimating ices. It was the first time we could study an interstellar object with enough detail to learn its chemistry. Astronomers discovered that Borisov contained more carbon monoxide than most comets in our solar system, suggesting it formed in a colder region around its parent star. But Borisov also taught us how fragile some interstellar travelers can be. It fragmented near perihelion, breaking into pieces that drifted apart like grains of sand. It came, it taught, and it dissolved. And now, in 2025, there is 3I Atlas, larger than Oumuamua, more stable than Borisov, stranger than either. Its behavior bridges the familiar and the unfamiliar. A comet, but with features that stretch our expectations. Volatile, but in unexpected patterns. Active, but shaped by a plasma environment far more organized than its tumbling nucleus would allow on its own. And unlike the first two visitors, 3I Atlas has encountered something neither of them did: a direct interaction with a CME. In that sense, it is the first interstellar object to truly touch our star on a dynamic level. The first to let us watch how material from another star responds to a solar storm from ours. Looking at these three objects side by side feels like watching a story unfold, with each chapter offering a new theme. Oumuamua taught us that interstellar objects exist. Borisov taught us that some carry ancient chemical fingerprints, and 3I Atlas teaches us that these travelers can interact with our sun in ways that reveal their inner structure. 3 visitors, 3 lessons, 3 glimpses into the deep processes that shape planetary systems across the galaxy. And yet, there are common threads among them. All 3 traveled alone through the darkness for unimaginable spans of time. All 3 preserved hints of their birthplace, shape, chemistry, behavior, even after tens of millions or billions of years. And all 3 remind you of something Carl Sagan said, something that feels especially true in this quiet moment. We are a way for the cosmos to know itself. These visitors aren't speaking, of course. They don't choose to travel here. But by observing them, by learning their stories, by tracing their paths, humanity becomes part of a much larger conversation. We watch the cosmos, and in doing so, we help the cosmos watch itself. As you reflect on that idea, the differences between the visitors begin to feel like variations on a shared theme. Oumuamua was the silent messenger. Borisov was the fragile emissary. 3I Atlas is the resilient traveler, the one that not only survived a close solar encounter, but also revealed new layers through the CME event. It is a reminder that no 2 interstellar objects are alike, just as no 2 planetary systems are alike. Each one is a unique expression of the physics, chemistry, and history of its home star. The strangeness of 3I Atlas doesn't make it an outlier. It makes it part of a growing spectrum, one that will only expand as our instruments improve and as more travelers cross our path. Interstellar objects are no longer rare theoretical curiosities. They are a new category of celestial neighbor, small in number but immense in significance. And each one leaves a subtle mark, not on the solar system, but on us. Because every visitor changes us a little. When you step back from the data, the images, the plasma physics, and the long arc of interstellar visitors, something quieter rises to the surface. Something that isn't about measurements or models at all. It's the way a story like this makes you feel. The way it places you inside the universe, not as an observer looking outward, but as a small part of something immeasurably vast. Because when you follow 3i Atlas across weeks and months, when you watch it survive perihelion and drift through the lingering breath of a CME, you can feel the scale of everything around you shift. The problems of the day shrink a little, the noise softens, and in that widening space, the universe becomes less of a distant scientific concept and more of a quiet companion, something ancient, patient, and steady, moving at a rhythm far slower than your own. You can't help but feel small in that perspective. But it's a comforting kind of smallness, not the kind that isolates, but the kind that frees you from the pressure to know everything, solve everything, or carry everything alone. The universe doesn't ask you to keep up with its scale. It doesn't demand that you understand every anomaly or interpret every signal. It simply invites you to notice, to look upward, to feel the calm that comes with recognizing that so much unfolds beyond you, and yet none of it asks anything of you. There is beauty in not knowing, in letting the unanswered questions remain open, like windows rather than walls. Some mysteries are not meant to be solved in one night or one lifetime. Some are meant to stay with you gently, giving your mind something soft to wonder about without urgency. 3i Atlas offers that kind of mystery. It doesn't disrupt your world, it expands it. As you listen, your thoughts slow a little. The story becomes less about an object moving through space and more about the way you move through your own life, day by day, moment by moment, carrying both curiosity and fatigue, both the desire to understand and the need to rest. In a strange way, 3i Atlas mirrors your own experience. It travels through light and darkness. It faces forces far larger than itself. It continues forward even when the path ahead is unknown. And it does so without rushing. There is a softness in that thought, something grounding, the realization that you too can move at your own pace. You too can let the unexplained remain unexplained for now. You don't need to decode the universe tonight. You don't need to solve the day you just lived. You only need to breathe, to listen, and to let the story settle around you like a blanket. Because the universe is not loud. It is not demanding. It is not in a hurry. It holds its mysteries the way a quiet room holds shadows, softly, patiently, without threat. And when you look at it this way, even the biggest questions feel less like challenges and more like invitations. Not to think harder, but to relax into the understanding that uncertainty is natural, that curiosity doesn't need to be answered immediately, that rest is part of learning. You feel that now, a shift from active attention to something gentler, more reflective. The science becomes a backdrop. The vastness becomes a comfort. And 3i Atlas becomes just one small light drifting through the dark, reminding you that not everything needs explanation to be meaningful. And yet, as vast as it is, you are safe. As the journey of 3i Atlas drifts into the distance, the intensity of the past weeks begins to soften. The brightening, the color shifts, the perihelion fire, the CME sweeping past, it all settles now into a calmer chapter. You can picture the object far from the sun's glare, its long tail thinning into the dark, its coma fading back into something quieter, gentler. The jets that once held their shape so sharply start to blur at the edges as the object moves into colder, calmer winds. Little by little, it leaves the turbulent inner solar system behind. Far closer to home, the solar storm that once raced toward it disperses into the endless flow of the solar wind. What was once a defined wave, tracked, modeled, anticipated, loses its shape, dissolving back into the steady breath of the sun. The CME becomes memory, its signature carried away into interplanetary space until even that faint trace vanishes. The storm ends not with a flash, but with a return to equilibrium, a quiet exhale. And in the control rooms where NASA watched every frame, the lights dim again. The urgency passes. The instruments continue their steady rhythm, collecting data, storing images, listening to the quiet hum of the universe. But the intensity softens. Screens that once displayed bright solar waves and wide cometary comas now show calmer fields. The scientists who traced every shift, every glow, every contour finally lean back a little. They know more than they did before. They also know there is still much they don't. But the night doesn't ask for answers. It simply asks them to rest, the same way it asks you. The universe itself feels slower now, as if settling into a gentler rhythm. Stars keep their steady pulses. The planets move without hurry. Even the sun, with all its power, seems to glow with a softer light as the hours drift forward. Everything that felt urgent becomes distant. Everything that felt strange becomes familiar in a quiet, cosmic way. You sense the stillness spreading outward, like ripples calming on a vast, dark lake. 3i Atlas continues on its path, unbothered by the questions left behind. It doesn't need us to understand it. It simply moves, at its own pace, through a universe that has been carrying travelers like it for billions of years. And somehow, that thought wraps around you like a blanket. It reminds you that not everything needs your attention right now. Not everything needs resolution tonight. Your breathing begins to match the slow rhythm of the cosmos. Deep, even, unforced. The story that brought you here has eased from curiosity into comfort. The boundaries of the day feel softer. The noise inside your mind fades into something quieter, gentler, easier to carry. There will always be mysteries. There will always be visitors from the dark. There will always be questions we follow into the night, but none of that demands anything from you now. The universe can hold its own stories for a while. It has been doing so long before you were here, and it will continue long after. Tonight, you're allowed to let go, to stop searching, to rest. Out there, 3i Atlas glides onward, smaller now in the telescope's eye, softer in its glow, fading into the quiet dark between the planets. It carries no urgency, no expectation. It simply travels, steady and peaceful, like a lantern drifting on a calm river. And here, in the stillness of your own room, the universe meets you in that same quiet. No rush, no noise. Just the calm of knowing that the cosmos continues its slow dance, whether or not you're watching. Good night, traveler.